In this video I'm going to be talking about arithmetic sequences and series. I'll talk about what they are and what we can do with them. So to begin with, I just want to talk about sequences. So you should already be familiar with sequences, and you will have seen many different types of sequences throughout schools. So for example, 1, 4, 7, 10. This sequence is made by adding 3 on each time to the previous term, and we could use a ... to represent that it goes on forever. We could have also had a sequence 1, 4, 9, 16, and again ... showed it goes on forever. And this sequence is actually all the square numbers, so 1 squared, 2 squared, 3 squared, 4 squared. We could even have a sequence that looks something like this, where you are just multiplying by -1 each time. And again, you can use a ... to show that it goes on forever. So sequences can take many different forms, but they are essentially just a list of ordered numbers. So a list of numbers that are in some kind of order and have some kind of rule. So a little bit of notation before we start talking about arithmetic sequences in particular is you might sometimes see something like this. So obviously this is just the counting numbers, and instead of just going on ... you might have ... n. This means it goes 1, 2, 3, 4 and carries on all the way up to n. So this sequence actually finishes. N is often used to count through the sequence as a counter, but it can also be used to represent the last term. So you have to be a bit careful with your definition of exactly what you're using n for, and we'll talk about that a little bit more in a minute so you understand what I'm talking about. So you might also see a 3 written, for example. That just means the third term of a sequence. So for example, you might see A1, A2, A3, A4, and so on, all the way up until AN, where that would be the nth term. So if we had a term that was 8 terms long, that would be A8. A1 is often just called A. So if you ever see A on its own, that means the first term. That's very important when dealing with arithmetic sequences and series, because we use A in our definitions and our rules. A is the first term. So A is the first term. A with a small subscript number means a certain term, so A3 would be the third term, A10 would be the 10th term, and AN means the nth term, which is often used as the last term of a sequence. An arithmetic sequence, or you might have heard it termed an arithmetic progression, or AP for short, is just a particular type of sequence. Now it's probably the simplest type of sequence that you can think of, in that it is just a sequence that goes up by the same amount each time. So for example, if I know my first terms are 1 and 2, to get from 1 to 2 you add 1, so I know I'm going to have to add 1 each time. So I would just continue adding 1 each time. So my sequence would be 1, 2, 3, 4, 5, 6, and so on. If I started with 3, 5, 7, 9, carried on, we know that we're adding 2 each time, so my next term would be 11, then 13, and so on. You could also start higher, and your numbers can go down. So this time we are going down in 3s, or adding -3 on each time, and we can continue on forever. It doesn't even have to go up in whole numbers. The difference doesn't have to be a whole number each time. So we could be going up in 1.4s, for example, so 5.2, and so on. So an arithmetic progression or an arithmetic sequence is simply a sequence of numbers in which the difference between each term is constant. So we're adding a constant on each time. So the definition of an arithmetic progression helps us to generalise it and come up with a set of rules for it. So like I said before, we use A to represent the first term of a sequence. So if our first term is A and we want to add a difference, a constant on each time, let's call that constant D for difference. So our next term would simply be A plus D. So remember, A is our first term and D is our common difference. So that's what we will be adding on between each term. So our third term then would be our second term, which is A plus D, plus another D. Our fourth term would be our third term, so a plus d plus another d. So hopefully you're starting to see what's going on. So if we simplify this sequence down, our first term is a, our second term is a plus d, we can't simplify that. Our third term, however, d plus d is 2d. Our fourth term would be a plus 3d. Our fifth term would be a plus 4d, and so on. Now remember I said before that n is often used as a counter, so it's used to represent the position in the sequence or what term you're on. So 1 would be the first term, in this case a, 2 represents our second term, our third term, fourth term, fifth term, and if we carry on, we could carry on all the way up to our nth term. And we often use a with a small subscript to show which term we're on. So a1 would be our first term, which we often just call a. a2 would be our second term, so that would be a plus d. a3 would be a plus 2d, and so on. It's important that you understand the difference between n and the nth term. So n is where it is in the sequence, or what term we are looking at, and the nth term is the value of that number in the sequence, what the actual number is. So if we continue with our pattern then, our first term is a, our second term is a plus 1d, our third term is a plus 2d, fourth term is a plus 3d, so hopefully we're seeing the pattern, and our nth term would actually be a plus, and then it's always 1 less d than the position. So our position is n, so it's 1 less than that, n minus 1, lots of d. Because our first term here has no d's in it, we just start at a and then we're adding on a d each time, so we've always added 1 less d than the position we're at. So this actually gives us our first rule for arithmetic progressions, is that our nth term, or an, is equal to our first term a plus n minus 1, which is 1 less than the position we're in, times d, which is our common difference of the sequence. So if you know your first term and the common difference, then you can actually find any term in the sequence without having to write out the whole sequence. So if I wanted to know my 50th term, as long as I knew my first term, I knew that I'd be adding a, starting at a, my first term, and adding on 49, which is 1 less than my position number 50, 49, lots of d. This gives us the value of any term in the sequence, providing we know our first term and our common difference each time. So let's have a look at some questions to see what we can do with this. So in this question, we are told that it is an arithmetic progression, so we know that our sequence will continue going up by the same difference each time, and we are asked to find the 7th term. So remember, that means we are asked to find a7, the value of the term that will be in the 7th position. So to start off with, we need to look at our sequence and decide on our first term, a, which is minus 2. Our first term is just the first number in the sequence, so minus 2. And our common difference is going to be the difference between minus 2 and 4. So 4 take away minus 2 is 6. And just to check, 4 plus 6 is 10, so that's our difference in the next two terms too. So a is minus 2 and d is 6. Now we know that our 7th term is going to be equal to our first term plus 6 lots, because it's always 1 less than the term number, 6 lots of d. If you can't remember that, remember our formula that we're using is our nth term is equal to a plus n minus 1 d, and n is our term number. So here, 7th term tells us that we are looking for the term in the 7th position, so n equals 7. So a7 is equal to a plus 6d, so a is minus 2 plus 6 times d, and d is 6. So minus 2 plus 36 is 34. So if we were to continue this sequence up to the 7th term, we would find that the term in the 7th position would be equal to 34. So for question number 2, we aren't actually given the sequence, but we are told the 4th term is 17, we're told the 7th term is 26, and again we are told that it is an arithmetic progression, so we know that the difference will be constant each time. So if we think about what this means, the fourth term is 17. So the fourth term, remember, means that n equals 4. And this time we are told the value of the term, so we know that a4 is equal to 17. And we are also told that our seventh term, so when n is 7, is equal to 26. So a7, the value of the seventh term, is 26. How does this 2 bits of information help us? Again, if you think about our formula, an equals the first term plus n minus 1 d. We know here then that 17, our fourth term, must have been equal to our first term plus 3d. And here our seventh term, 26, must have been equal to a plus 6d. So then we've got a case of simultaneous equations. So if I write out my 2 equations underneath each other, this is where it helps if you know how to do simultaneous equations. If you can't remember how to do that, I do have a video on that. But for now, we are going to use elimination and do equation 1 take away equation 2. So 26 take away 17 gives us 9. A take away A cancels out, and 6d take away 3d is 3d. So we've got this equation here, the 9 equals 3d, from using our formula for the nth term, which is an, and plugging it in for the 2 terms that we know, and then using simultaneous equations. But if we think about what this actually means, this means that 3 lots of d, 3 lots of the difference, is 9. If we go back to our question, we were told the 4th term and the 7th term. That means that to get from the 4th term, we go the 5th, the 6th, the 7th. So we add on the difference 3 times, which is our 3d. And the difference between our 2 terms, 17 and 26, is 9. So we could have got straight to this equation from the question, but it's good to do it using simultaneous equations because it's easy to make mistakes in your head, but then check that it makes sense. Check, does it make sense that 3 lots of the difference is equal to 9? In this case it does. So the difference is 3. So we now know that we've got an arithmetic progression that goes up in 3s. And now we know that, I'm going to use equation 2 here and say that 17 must be equal to a plus 3 lots of d, which we now know is 3. So 17 is equal to a plus 9, meaning that a, our first term, must have been 8. So we now know our first term must have been 8, and our difference each time is 3. So our 10th term is going to be equal to a plus 9d, because remember it's always 1 less than the term number, which is 8 plus 9 times 3, 27 add 8 is 35. So our 10th term would actually be 35. Our third question is slightly different again. This time we are given our sequence, but we're not asked to find a particular term. We are asked to find which term is equal to this. So we know the value of the term, so we know an, and we are trying to find n. We are trying to find where in the sequence that will be. So again, looking at our sequence, we know that a is 11, our first term, and this time the difference is minus 2 because we are going down by 2 each time. So we know that our nth term will be equal to a plus n minus 1, always 1 less than the term number d. And in this case we know the value of our term, so we know an. We know a. We don't, however, know n. That's what we're trying to find. We are trying to find the term number, but we do know that d is minus 2. So I'm going to take 11 away, so minus 24 equals minus 2 lots of n minus 1. Divide by minus 2 gives me 12 is n minus 1. Add the 1, so my n is 13, which tells me that the 13th term, so remember n is what term number, where it is in the sequence, so the 13th term is actually equal to minus 13. So test yourself, pause the video and see if you can answer these questions, and I will give you the answer in a second. So for number 1 we are given the sequence, so from that we know the first term a is equal to minus 4, and we know the difference each time is going to be equal to 6. We need to add 6 on each time to get to the next term. So our 9th term, a9, is going to be equal to a plus 8d, because 1 less than the term number each time, so minus 4 plus 8 times 6 is 44, and our 17th term is going to be equal to our first term plus 16 differences. So minus 4 plus 16 times 6. So minus 4 plus 16 times 6 is 92. So our 9th term will be 44 and our 17th term will be 92. So for question 2, we aren't told the arithmetic progression, but we are told the 9th term and the 5th term. So our 5th term tells us that when n equals 5, the term number a5 is equal to 31, and the 9th term, so when n equals 9, a9, the 9th term is equal to 19. So we can put this into two equations. So we know that our 5th term 31 is actually equal to a plus 4 lots of d, and our 9th term 19 is actually equal to a plus 8 lots of d. So if I call it equation 1 and equation 2 take away equation 1 gives us 19 minus 31, which is minus 12, and that will be equal to 8 take away 4, so 4d. And again, if we look back at our question to check that this equation here makes sense, we've got our 5th term and our 9th term. So to get from the 5th term to the 9th term, we need to add on 4 lots of our difference. And then the terms go from 31 to 19. So this time you have to take away 12 to get from the 5th to the 9th term. So it makes sense that 4 lots of our difference is equal to minus 12. So our difference each time is minus 12 divided by 4, which is minus 3. So if we know that our difference each time is minus 3, we can go back to equation 1 and say that 31 is equal to our first term plus 4 lots of minus 3. So 31 is equal to a minus 12. So a is equal to 43. So now we've got our first term and our common difference, we could actually work out any term in the sequence. We are asked to find our 20th term. So our 20th term is equal to a plus 19d. So a is 43, and then it's going to be minus 3 lots of 19, which is minus 14. So even if you aren't told the whole sequence, if you know it's an arithmetic progression and we've got 2 of the terms, you can actually find out any other term in that sequence. Let's have a quick look at number 3 then. So in number 3 we do know our first term is 2, and we do know our difference this time is 2.5. We are asked to find which term is equal to 47. Now remember, that's not n, that's an. So we know an is 47, but which term is asking us to find n, so we don't yet know what n is, but we do know that 47 is equal to our first term a, which is 2, plus n minus 1. We don't yet know n, remember, but n minus 1 lots of our difference, so n minus 1 lots of 2.5. So 47 take away 2 is 45, and that's equal to 2.5 n minus 1. So n minus 1 is equal to 45 divided by 2.5, which is 18. And that gives us then that n is 19. So if we were to continue on with this sequence here, our 19th term would be equal to 47. Now I hope you now understand what an arithmetic sequence or arithmetic progression is, but the other thing that is often of particular importance is an arithmetic series. Now what we mean by series is the sum of the terms of a sequence. So for example, instead of having the sequence 1, 3, 5, 7, 9, which would be a sequence, a series is simply the sum of each of the terms. So 1 plus 3 plus 5 plus 7 plus 9, and so on. So when we are talking about an arithmetic series, we are talking about the sum of all the terms of an arithmetic sequence. So a series is often written out as a sum of lots of different numbers, but if you actually know all of the terms, it gives you a single answer. It's the sum of all those terms rather than a list of numbers, which is what a sequence is. So let's have a look at that in terms of our arithmetic series. Now, we've already discussed what the terms of an arithmetic sequence would be. So our first term is always a, then we would have a plus our difference, then a plus 2 lots of our difference, a plus 3 lots of our difference, and so on, all the way up to our last term. Now, I've used L here to simply represent the last term if we have a series that is n terms long, so is not indefinite. And if we knew how many terms we had, we could actually find out the value of that term. But for now, we'll just use L, and we'll discuss that in more detail later. Remember, we said that a series is achieved by simply adding up all the individual terms of a sequence. So simply by putting plus signs between and adding up each term. Now, we often use Sn to represent the sum of the first n terms. So if you want the sum of the first n terms, we use Sn, so S with a little 12 would mean the sum of the first 12 terms. Now that's important because if the numbers are getting bigger each time, then your answer will just get bigger and bigger and bigger. You can't continue to keep summing it. You need some sort of end to the sequence. So it's important you know how many terms you want to sum. So the sum of the first terms Sn is equal to each individual term added together. So luckily we don't actually have to work out every single term of a sequence and add them up. That would be very time consuming and tedious, especially if we had a lot of terms. So there is actually a trick of how we can do it. And the first thing to do is write out the same sequence backwards, so the same series backwards. So we again want to write out the exact same thing for Sn, but this time we're going to start with our last term and write all the terms out backwards directly underneath, but we are going to start from our last term all the way to our first term. So if we started at our last term, our next term would be L minus D because we're going down the sequence instead of up the sequence. So our third term would be L minus 2D, our fourth term would be L minus 3D, and so on until we get to our final term, which is actually A. So now the clever bit, or the trick, is to actually add these two sequences together. So instead of finding the sum of one sequence, we will be finding the sum of two sequences. So it will be 2 Sn, so 2 lots of the sum of our first n terms. And because we're adding all of the terms in the top sequence to all of the terms in the second sequence, we can add them in any order we like. And the reason we've written them as we have with the second sequence written out backwards is if you look what happens if we combine each or simplify each of the vertical pairs of terms. So A add L is A plus L. A plus D plus L minus D. The plus D and minus D cancel out, so we're left with A plus L. In our third pair of terms, the plus 2D and minus 2D cancel out, again leaving us with A plus L. Same thing would happen in our fourth term, all the way to our final terms, which again are just A plus L. So don't forget we are actually adding all these together. But hopefully you can see that every single term is the same. And if our sequence was n terms long, remember we wanted the sum of the first n terms, we actually have n lots of A plus L. So 2 lots of our sequence would be equal to n lots of the first term plus the last term. We don't want 2 lots of our sequence, we just want 1, so we just simply need to half it. So half of n lots of A plus L, which if you think about it makes sense, because if you think about a simple sequence, the counting numbers 1, 2, 3, 4 all the way up to 100. If we add up the first and last term, which would be 100 add 1, we've got 101. the second and second to last term, 2 plus 99 would be 101. 98 plus 3 would be 101. So they'd all add up to 101. But we've worked from both ends inwards, so we would only have 50 terms to add up rather than 100 terms to add up. Now, if you don't understand that, but you don't need to worry too much, as long as you're happy with using this formula. And you may actually see this formula written in a slightly different way, because remember, our last term was what we meant by L. And if we are summing the first n terms of a sequence, our last term is actually equal to our nth term, which is a plus n minus 1 d, from our definition earlier of the arithmetic sequence. So we can actually substitute in a plus n minus 1d for our L here, which would give us n over 2. A plus a would be 2a plus n minus 1d. So you may have seen it written in either of those forms. They are both the same thing. It just depends whether you already know your last term or whether you know your first term and your difference. But you could use either formula depending on which one you prefer. So let's have a look at some questions and how we can use this. So in this question we are asked to find the sum of the first 30 terms. So we are asked to find S30, the sum of the first 30 terms. And we know the first term and the common difference, but we don't know the last term. You could work out the last term, which would be the 30th term, or you could use the second formula we derived, which was n over 2 lots of 2a plus n minus 1d. So S30 means 30 terms, so we're going to use n is 30, so 30 over 2 lots of 2 times a, our first term in our sequence is 1, so 2 times 1, plus n minus 1, which is 29, because remember we're using 30 terms, and our difference is 2, so 29 lots of 2. So 30 over 2 is 15, lots of 2 plus 2 lots of 29 is 58, so 15 times 60, which is 900. So our first 30 terms of this sequence would actually add up to 900. So for our second question, again we are told an arithmetic progression 15, 11, 7, 3, and we are asked this time how many terms we need to get a sum of minus 240. So we don't know how many terms we are summing, but we know that the sum of those n terms is equal to minus 240. So again, I'm going to be using the formula in the second format that we derived, and this time we know Sn, so we know Sn, but we don't yet know what n is. We do, however, looking at our sequence, know that our first term a is equal to 15, and that our difference each time is minus 4. So substituting what we do know into our formula, the sum of the n terms minus 240 is equal to n over 2, we don't yet know n, lots of 2a, which is 30, 2 lots of 15 is 30, plus n minus 1 lots of d, which is minus 4. So I'm going to multiply by 2 first to get rid of my fraction, and I'm going to expand inside my brackets. So n times minus 4 is minus 4n, minus 1 times minus 4 is plus 4, and then I'm going to expand and simplify at the same time. So 30 plus 4 is 34, so I've got 34n minus 4n squared equal to minus 480. Now I have done 2 steps in one at this point, so just to reiterate where this has come from, I've simplified within the bracket, so I've done 30 add 4 to get my 34, and then I've multiplied the whole bracket by n to expand out the brackets. So 34 times n is the 34n, and then n times minus 4n gives me my minus 4n squared. Now I can see here that I have a quadratic equation. We know that to solve any quadratic we need it to be equal to 0, so I'm going to move everything to the left hand side of my equation, so 4n squared minus 34n minus 480 is equal to 0. Now I can actually see that I can divide 3 by 2 to get 2n squared minus 17n minus 240 equals 0. Now, because this equation has an n squared term and an n term in it, it is a quadratic equation. If you can't remember how to solve quadratics, then look at my video on that. But for now, we are just going to continue and solve this as we would any normal quadratic equation. Now, this is quite a tricky one to factorise, so you could solve it using the quadratic formula, but it does actually factorise into 2n plus 15 times n minus 16, and that equals 0. So from that we can see that n is either equal to minus 15 over 2 or minus 7.5, or n is equal to 16. Now remember that we are looking for how many terms. It doesn't make sense to have minus 7.5 terms. You can't physically have that. So our answer is 16. So in this case our one answer didn't make sense because it was minus 7.5. However, you will get the odd occasion where you get two valid answers. So if we got two answers that were both whole numbers and positive, they would have both been completely valid, and either of them could have been our answer. There would have been two possible sequences that fitted our criteria. In this case, however, the minus 15 over 2 or minus 7.5 isn't a valid answer, so our answer is 16. So we would actually need 16 terms for the sum of all those 16 terms to equal minus 240. So test yourself, check that you really understand this, pause the video and have a go at these three questions. So to find the sum of the first 25 terms of an AP, again I'm going to use our formula in the second format, 2a plus n minus 1d, and this time I know that a is minus 8 and d is plus 2 because it's getting too big at each time. So the sum of my first 25 terms is equal to 25 over 2, lots of 2 times minus 8 is minus 16, plus n minus 1 is 24, so 24 lots of 2. So that's equal to 25 over 2 lots of minus 16 plus 48, so 25 over 2 lots of 32, so 16 times 25 is 400. So number 2, the counting number, remember, is just an arithmetic progression with a difference each time of 1. So in this case, we already know that a is 1, we already know that our last term, L, is 100. So I'm actually going to use the sum formula in the first one, the first format that we derived, which was n over 2 times the sum of the first plus the last. So n, I want the counting numbers from 1 to 100, so I actually want the first 100 terms. So 100 over 2 times my first term 1 plus my last term 100. So it's actually 50 lots of 101, so 5,050. My third question then, this time we are told some relationships, so we need to set up some equations first. So firstly we're told that the sum of the first 10 terms, which is S10, is triple the sum of the first 5 terms. So we know that that's 3 lots of the sum of the first 5 terms. We're also told that the sum of the first 3 terms, so S3, is equal to 15. So this looks quite tricky, but let's see what we can do with this information. Now I'm going to be using the formula in the second format again, which is the one up here, Sn equals n over 2 to a plus n minus 1d. So S10 is going to be equal to 10 over 2, which is 5, lots of 2a, we don't yet know a, plus n minus 1, so 9 lots of d, and that is going to be equal to 3 times S5, so 3 lots of 5 over 2, n over 2, lots of 2a plus 4d. So all we've done here is we've said, well, we know that the 10th term, and we've plugged in what we know into this formula up here, is equal to 3 lots of the 5th term, and again we've plugged in everything we know into the formula up here. So a bit of simplification and rearranging of that. So I can see that the 5's cancel out, and if I multiply through by the 2 on the right hand side, that will give me 4a plus 18d is equal to 6a plus 12d. And then if I move all my a's to the right hand side and all my d's to the left hand side, I get 6d equals 2a, which can simplify even further to a equals 3d. So that doesn't yet give me enough information, but I was also told that S3 equals 15. Remember, the sum of the first 3 terms is going to be 3 over 2 lots of 2a plus 2d, and that is equal to 15. Now I know that a is equal to 3d, so I can substitute that into this equation for a. So I know that 3 over 2 lots of 2a, which is 3d, so 6d, plus 2d equals 15. Now if I multiply by 2 over 3, that gives me 8d equals 10. So d is 10 over 8, which is 1.25. Now remember, we have already found a relationship for a in terms of d, which is the relationship down here that a is equal to 3d. So we can now use that to find a. So now I know d, which means that a is 3 times d, so 3.75. So our first term of this sequence would be 3.75, and our difference each time would be 1.25. Now this question was slightly more difficult because you had to set up the equations, do a bit of substitution and rearranging, but all the information was there. As long as you are clear in the difference between the term and the term number and can use the formula that we have produced, then you should be able to work out the answer to any of these questions. So I hope you now understand arithmetic sequences and series. Another important progression that is studied is the geometric progression, or geometric sequence, and the geometric series. So have a look at my video on that. Good job, and I'll see you again soon.